Thank you, Professor Yao, for the introduction and also for the invitation. So I'm actually very pleased to and also honored to give to have some sharing of our recent works. So today, my topics I think is very similar to the one delivered by Professor Ji, because we are working on the complex interfaces. But in my work, I mainly focus on the droplet dynamics. Okay, so in this talk, I will major introduce the impact dynamics of the droplets onto a solid surface. So for this kind of situation, it is a very ubiquitous process in many and natural processes, such as in the spray cooling. In the spray cooling for the electronic devices and also in the power plants, we typically release the liquid hot solid walls, and then the droplet will evaporate. So by the evaporation, the droplet will take away some heat, so that to achieve the efficient cooling. So during this process, the basic droplet, the basic process is that liquid droplet impact onto a solid surface. And also in the combustion engine, we have the spray of the droplet from the nozzle, and after those tiny sprayed, they can undergo an ignition to combat with flames and also temperature change. And sometimes those droplets, they can impact onto the solid wall of the engine. It also involves the droplet impact dynamics. And also in other applications includes the inkjet printing or 3D printing. We release some droplet onto a moving solid substrate so that some patterns can be created. In the agricultural spray, these Capillary solutions will be sprayed into droplets, and those droplets, they are deposited onto the surface of the plants, sometimes on the leaves, sometimes on the soils. So we see that so many processes, the deposition or the impact process of the droplet. So achieve a deep understanding on the dynamics and processes of the droplet impact is very crucial to improve these applications. So this is the background for my research. And when I am entering into this field, I go to the literature to see what has already been achieved over the, for example, the past decade. Notice that with the development of the micro and nano fabrication technology, people have done a lot of work regarding the surface engineering. So a lot of works have been focused on creating surfaces with different physical properties and also chemical compositions, so that with this engineered surface, the droplet behaviors, for example, in this paper, macroscopic extrusions was created on a solid surface, so that when a droplet impact onto this so-called ridge surface, the droplet will be split up into two or more daughter droplets, so that it can engineer the contact time between the droplet and the solid surface, and also by engineering the temperature of the solid surface and also the surface hydrophobicity and the hydrophilicity patterns on the solid surface, people can achieve different behaviors. For example, to enhance the bouncing of the droplets or to inhibit the bouncing of the droplets. So this will have the practical applications. For example, in the inkjet printing and the agricultural spraying, we would like to have the droplet to stay on the solid surface when they impact onto it. However, in the liquid spray, in the combustion engine, we would like to avoid the sticking of the fuel droplets onto the walls, so that to enhance the combustion efficiency. So this means that we would like to study the dynamics of the droplet impact, so as to propose some effective strategy to tune or to manipulate the outcomes of the droplet impact. So this is the thing we would like to achieve, and And when we are considering a basic process for droplet impact, actually, for a lot of studies, the single droplet or the Newtonian liquids, they have been used. And for this kind of process, a lot of works have been done. So our understanding has already been comprehensive. And the basic energy transition conversion process is very clear. So initially, the droplet is released from a height with some kinetic energy. And then this kinetic energy was converted into the surface energy by the droplet shape deformation. And then with the and then this surface energy will restored to the kinetic energy so that the droplet will again bounce up. So this is a very typical droplet impact and deform and take off process. So this process they usually happens on the super hydrophobic surface. So for example, here we have the video shows up here. This droplet, they just dance on this solid surface. And when we look at this process, I noticed that when we are modeling the dynamics of the droplet impact, we typically treat these droplets as a homogeneous liquid, or to treat the simple liquid as a very simple Newtonian liquid. Means that we treat the surface the surface tension and viscosity and all the other physical chemical properties to be uniform along the droplet surface. So, and then when we are considering the capillary effect, they are usually uniform and isotropic, means that we model this droplet to be spherical, and the effect of the capillary force will be symmetric to each other. So this is the normal case when we're dealing with the simple droplet impact case. However, in practice, the liquid is not so simple. So in many cases, they are Newtonian. And also in other cases, their properties can be changing with the environment. For example, in the combustion process, the droplet is burning and temperature can change. So in this process, the surface tension, the properties of the droplet is more complicated. So, and then naturally there is a very fundamental scientific question occurs. So means that can the capillary effects be anisotropic during the droplet impact? And if so, how can we achieve that? And how can we understand the behaviors induced by this anisotropic capillary effect? Okay, so today I'm going to share with I think here 3 examples. Okay, so in the first example, we introduced the gas liquid hollow droplet. So this is a compound droplet with the core shell structure. And in the second case, I will introduce the impact dynamics of the solid liquid core shell structure. We call this as a particle latent droplet. And in the third case, we use a simple fuel liquid, but this fuel is in an burning state. So we call this a burning droplet or the hot droplet. So this is the 3 cases that we identify the anisotropic capillary effects. Okay, so in order to create this compound droplet, the gas liquid and solid liquid droplet, so here we use a microfluidic technology. So with this technology, we can produce the different compositions and structures. For example, the Janus droplets with 2 phases and core shell droplets with tunable compositions of the core material and the shell materials. And also we can use these materials, these droplets as template to produce the super hydrophobic surface. So this super hydrophobic surface in our study to achieve the impact case. Okay, so so now in this first example, we create this hollow droplet. So in this hollow droplet, the inner core is a gas core. So the outer layer is a liquid shell. So we release this so-called hollow droplet onto a super hydrophobic surface. And we compare it with the simple droplet impact. We found that very interestingly, on the same surface with the same mass and also with the same initial kinetic energy of the droplet, the hollow droplet cannot bounce up. But instead, here we see that this, we call this simple droplet as the single phase droplet. So this droplet is, as the normal case, it bounces up very readily. So we are very interested with this phenomena because the surface we're using is the superhydrophobic surface. We should expect that all the liquid droplet is now waiting on the surface, and then it can bounce off. However, we repeat this experiment for many times, and also by using different liquids. For example, we use the gas in water, gas in oil, and also to put this liquid droplet under another liquid. So here on this video shows, we also release a bubble enclosed, so a hollow droplet under the liquid to impact a solid wall showing up here, so they cannot bounce. And also we tilt the surface. And also in the Leidenfrost, in many cases, the hollow droplet cannot bounce. So we notice that the bouncing behavior of the hollow droplet is suppressed. So we are interested about the mechanism and also their characteristics. So firstly, we studied their characteristics. We focus on three major parameters. One is the spreading parameter, beta. We defined as the maximum droplet diameter divided by its initial diameter. Okay, and another is the V retraction, the retraction velocity of the droplet. And also the final is the epsilon. Epsilon is the restitution coefficient, means that the droplet kinetic energy after takeoff, the ratio of the kinetic energy energy after takeoff to its initial state. Okay, so we has built a unified theoretical model based on the classical model to use two groups of non-dimensional parameters. One is the very famous Weber number, and in addition to this, we introduced another phase ratio of the bubble to understand this problem. So this phi. So we found that with this unified model, we can describe both the single phase droplet and the hollow droplet behavior. For example, when phi equals 0, all this model restores to the classical model used to describe the simple water droplet impact process. Okay, so this is the first thing we done. We developed a theoretical model by using scaling analysis to describe our system. And then what we are more interested about is how can this phenomena can occur? So actually in the literature, a lot of people have achieved the suppressed bouncing of the liquid droplet, but what they used is to dissipate the total system and the total system energy. So that means that the kinetic energy of the droplet will be greatly reduced, so that the droplet cannot have enough takeoff velocity, and then they will stay on the solid surface. And by using numerical simulation, we modeled our single phase droplet impact process and the hollow droplet impact process. The very first thing we check is how much energy is lost during the impact process. And very striking, we found that in this hollow droplet case, the energy loss is lower than 1%, and even smaller than the energy loss for the simple droplet. So this means that in our hollow droplet system, the energy dissipation is negligible. So it means that the droplet can still have enough kinetic energy. And then where does this kinetic energy go? Why those kinetic energy cannot be responsible for the droplet takeoff? So in order to answer this question, we look into the flow field for the droplet. So for this single droplet, we see that the flow field is, so for example, a very unified vertical flow field occurs after the droplet bounce, so that the droplet can take off. However, for this hollow droplet, we notice that the flow, so here again, it shows the simple droplet. But for the hollow droplet, we see that this liquid, the flow field is oscillating on the bottom of the droplet. So it means that this droplet, the liquid would like to go up. However, the presence of the inner gas liquid interface prevent the liquid to go upward. so that the liquid can have no way to go, but instead to turn the direction of the flow, so go back. So in this case, the flow filter is going up and upper and lower, upward, downward, upward, and downward, just in an oscillating process. So this means that the total kinetic energy of the system is preserved. However, the effective momentum is reduced, greatly reduced in the vertical direction, so that the droplet cannot have enough momentum for the takeoff. So we model this process by proposing a double spring system. We model the inner bubble interface as one spring and outer droplet interface as another spring. So these two springs, they are actually composing with each other. So it means that when one spring is stretching, another is compressing, so that the droplet, the kinetic energy is always absorbed by the deformation of the surface. So here we can see that the outer surface is stretching, the inner surface is contraction. So we modeled the SO and SI. SO is the inner surface area. O is the outer surface area. The change of them, they are in the antiphase. So one increase, another decrease. So this means that all the kinetic energy was absorbed by the deformation of the surface energy, so that the effective momentum is greatly reduced. So this is the mechanism responsible for the inhibited takeoff of the hollow droplet. And following this same principle, we found that actually in the macroscopic system, we can create the same thing. So we model this by using a water balloon. So for this balloon, it is a single phase balloon filled with water, so that it can bounce off. However, for this hollow balloon, inside this balloon, we create another gas-filled balloon so that it has two interfaces. So these two interfaces, elastic interfaces, they are composing with each other. So they also have two opposing springs, so that this hollow balloon cannot bounce up. So this means that this phenomena is not only dominated by the capillary effect, but instead any system with the counteractive elastic springs can also achieve the similar thing. And by following this principle, we're using the scaling analysis to derive the critical boundaries for the transitions between rebound and non-rebound. Non-rebound means that the droplet will stay on the solid surface. Okay, so here our scaling analysis agrees well with the experimental data. Yeah, so this is the first part, and further we include a pair of bubbles into the droplet. We found that with two identical bubbles, the symmetry of the droplet impact has been broken. Means that during this double bubble droplet impact, we observe simultaneously the spreading and the receding process. Means that, for example, here on this image, it shows that some interface, for example, the bubble side, here is the bubble side, is still spreading. However, in the liquid film side, indicated by these blue arrows, they start to receding. So on this system, one part is spreading, another part they are receding. So this spring cannot be a uniform spring, but instead a very representative feature for the anisotropic capillary effects. So we found that with this kind of anisotropic effect, the contact time is reduced by 60% when the droplet can bounce off. And also based on this anisotropic modeling process, we recalculate the contact time to define a non-dimensional ratio number n to consider the anisotropy of the spring. Okay, so and we can successfully account for all the observed contact time data during our experiment. So this means that when bubble are included inside the droplet, the anisotropy occurs. And the droplet cannot be modeled by using a single spring, but instead multiple spring and anisotropic spring system should be developed to account for the dynamic behaviors of those hollow droplets. So this is the first part, to include the bubbles. And further, we after finishing this work, we think that given that the bubbles can alter the droplet dynamics so much, and how about we change the materials inside? So we replace the bubbles by solid particles. And also we compare we call this particle-laden droplets. We compare these particle-laden droplets with the single droplets in the impact behaviors. And in this case, very different from the hollow droplet, the particle-laden droplets, they shows a very enhanced bounce behavior. So we are interested with the contact time here. So for an liquid droplet, the typical contact time is on the order of 10 millimeters. So this time is determined by the inertia capillary time scale. And for a millimeter sized droplet, time is on the order of milliseconds. Actually, over the past 2 decades, a lot of works have been devoted to reduce the contact time because it is related to the heat transfer process and icing process. However, limited by this inertia capillary time scale, the minimum contact time achieved to date was still on the order of milliseconds. So for example, larger than 1 millisecond or 2 milliseconds. There is no way to further reduce this contact time because they are limited by the capillary effects. However, in our particle-laden droplets, we found for the first time the contact time is smaller than 1 millimeter. So in this case, we use an elastic particle, a PDMS particle here. It achieves 0.3 milliseconds. And we further test the glass bead. So we include the glass particles inside the droplet. And we found that the contact time can be further reduced to 0.03 milliseconds, means that 10 times lower than the PDMS particles. So this is very striking data and result. And so we are very interested with this phenomena. So we further investigate how the contact time can depend on the impact velocity of the system, and also different from the conventional study. Our contact time TC has a 3 regime dependence on the impact velocity. However, when in previous studies using simple droplets, the contact time is a constant. So it is only determined by this inertia capillary time scale. Means that the TC does not depend on V using single droplet. So this means that new physics occur for these particle-laden droplets. So we studied these 3 regimes one by one. We found that in the relatively low impact velocity, the contact is based on the solid contact. So here the bottom is the encapsulated solid particles. So the liquid droplet cannot have enough inertial energy to deform and to go downward to touch the bottom surface. So in this case, the solid contact dominant over the process. And we model this process. We calculate the contact time by using the modified Hertz law. So here is the modified scaling analysis for the contact time. So on the right-hand side, it is the scaling derived from the Hertz law. So our modified Hertz law agrees well with the experimental data. So this also explains why we can achieve a so low contact time, because in this regime, it is determined by the solid dynamics instead of liquid fluid dynamics. So it means that the capillary effect disappear in this regime, so that the contact time can be reduced further because it shifts to another totally different regime. And based on this, we slightly increase the impact of it. Now, in this case, liquid shell can have enough kinetic energy to deform and to go downward to touch the solid surface. However, we found that this receding droplet film is not so this can be seen from this figure. So this RC indicate the receding dynamics, receding radius of the liquid droplet. So we see that at some time instant, suddenly the radius will changes from that the droplet will suddenly take off its whole surface from the surface, its whole bottom surface. So this we found that is due to that in this case, even though the liquid is touching the solid surface, however, the solid still has an influence on the droplet dynamics. And here we found that the particle takeoff velocity is identical to the liquid receding. Means that the liquid receding is induced. So here is the VP go upward, receding is from the radially to the inside. So this VP dominate over the VR. They are identical to each other. So that when the particle totally leaves the surface, the VR is also totally lift off the solid surface. Okay, so in this case, we call it as a mixed regime. Means that both the solid dynamics and the liquid capillary effect dominant over the droplet behaviors. So so this is the second regime. We have observed the solid liquid coupling behavior, and by further increasing the impact velocity of the droplet, we found that the influence of the particle can finally disappear. So in this case, we found that the droplet, the liquid shell can touch the solid surface, and also in the receding process, the liquid bottom can achieve a complete retraction or a complete receding. So this is reflected by the dynamical evolution of the RC. So it gradually changes from a non-zero value to zero value. However, in this case, again, the contact time is reduced. So, but here we account for the effective mass of the liquid. So we can still use the inertial capillary time scale to explain our data. However, depending on the volume fraction of the particles, the mass of the liquid shell will be different. So in this case, the contact time is still a function of the solid fraction of the particles. So yeah, and also we found that in this regime, given that the particle is not dominant over the liquid receding process, we found that the VP is separating away from the VR. Means that they are not identical to each other, and the VR is a constant value. So this constant value is determined by the inertia, by the capillary effect only. So as we observe the separation between solid dynamics and liquid and fluid dynamics. So in this regime 3. So we have achieved this 3 regime, and also by balancing the kinetic energy and the surface energy and also the viscous dissipation motion, we determine the 2 critical boundaries. One is here. So we see that starting from a given volume the system, by increasing the velocity or increasing the Webb number of the droplet impact, we can successively observe this Hertz regime, partial retraction regime, and complete retraction regime. So Hertz regime, the solid dynamics dominate. Partial regime, both solid and liquid coupling together, and in the complete retraction regime is purely capillary, the capillary dominant regime. Okay, and further we also tested the icing droplet. So because in practice, when we are considering the anti-icing process, for example, an airplane is flying in the planet in some for example, the icing the icing raining days and some other cases all in the cloud. Sometimes the liquid droplet, they are not purely droplets, but instead they are compound state, okay, with a solid ice core and the liquid droplet shell. So we studied the impact dynamics for this compound icing droplet. We found the same dynamics as our particle-laden droplet. Means that the contact time for this icing droplet can greatly be reduced from the capillary regime to the Hertz regime when the volume fraction of the icing core is large enough. So this will inspire us to rethinking about the anti-icing process, especially in the practical scenarios when the some solid liquid droplets, compound droplets that are encountered and when they impact onto the surface. So here we summarize the content time study over the past 2 decades. So as we said, in the capillary dominated regime, people can only reduce this non-dimensional content time by, for example, within 1 decade. However, our work can reduce the content time by at least 2 orders of magnitude and achieved the lowest record to date. So I personally very excited about this. By simply including solid particles into a liquid shell, we can achieve very significant change. So this is the second example to show that the capillary effect is not isotropic over the droplet dynamics. And in my last work to share today, we used a simple droplet, but here we ignite the droplet. The liquid fuel we initially tested, so on this video, show is the hexane decay. So we compare the impact dynamics of a burning hexane decay droplet with a non-burning room temperature hexane decay droplet. They are released from the same height with the same mass, and we found that compared to the normal droplet case, the burning droplet is bouncing away from the superhydrophilic surface. So here we use a superhydrophilic surface. We expect the droplet to stay or to stick onto the surface. However, the burning droplet, they didn't do that. And after bouncing, the burning droplet behaves like the bouncing droplet on a superhydrophobic surface. So we are very interested about what happens here. So why a burning droplet cannot stick onto the surface, but instead. So we initially guessed it could probably be due to the combustion of the, because we can see the flame here, the temperature of the droplet is changing. We have the phase change process, the fuel to evaporate, and also again to condensate on the solid surface, and also new gas has been produced by the chemical reactions during the combustion. So a lot of physical and chemical processes involved, and it makes this problem very tricky and very complicated to understand. And then we very luckily we found that when this burning droplet touch, we see some misty layer formed, for example, showing up here. So we see a ring of a misty showing up here. And I realized that this misty, they are condensed vapor, they are condensed vapor of the N-hexane decay. So we film the process from the bottom and to take a picture after the burning droplet is bouncing away from the solid surface. We do notice, for example, here a thin gel left on the solid substrate. So it means that on the bottom of the droplet, the vapor is condensing. So this means that this vapor is not burning locally, at least locally at the bottom of the surface. So only the upper vapor, they are in a burning state. So this gives us inspiration is that this burning droplet can probably be modeled in the same way as a hot droplet, because the hot droplet is not burning, and but the hot droplet has a high temperature and also has vapor released and also have the vapor condensation. And then we repeat the same experiment by using the hot droplet. We change the temperature of the droplet, and we found that there is a critical Webb number that discern between the bouncing case and the pinning case. So when the Webb number is lower than a critical value, we can observe bouncing. And this critical value is increasing when the droplet temperature increase. So this gives us some idea that the dynamics of the enhanced bouncing for the burning droplet should probably be identical to that responsible for the hot droplet. And to further verify our assumption, we extend our experiment by using multiple liquids. For example, we use silicon oils, soybean oils, use different oils in the hot state to create the hot droplet. We observe the same enhanced bouncing behavior. So we then investigate this problem by focus on the dynamics of the hot droplet. The first thing we do is to use the laser in the laser interference technology to visualize the bottom gas film. So when a liquid droplet touch, they stick onto the solid surface. For example, here the normal droplet here, the bottom film they will collapse. So here this black region means that the collapse around the film, and then it propagates. So this collapsed film is responsible for the sticking of the droplet onto the solid surface. However, when we observe the burning droplet and the hot droplet, we can see that the film is always there. Okay, even though this burning droplet, the film is distorted by the burning state of the droplet, by the combustion or by the released gas. However, when we look at the hot droplet case, we see a very stable, a very beauty gas film. And we compare the hot droplet case with the normal droplet case. So is one difference. Another difference is that the hot droplet, we can see that this Newton pattern is initially symmetric. However, when time goes on, it gradually evolves into asymmetrical patterns. However, in normal droplet, this Newton pattern is always symmetric. So for this normal droplet, it is consistent with the studies in the previous literatures. However, for the hot droplet, we observe the asymmetrical patterns. This has never been reported. So we are very interested about what happens here. So now, until now, we are clear about the fundamental dynamics is that for hot droplet and burning droplet, the reason why the bouncing is enhanced is that the gas film is stabilized. However, the question remains to be why this film is stabilized for the burning droplet. We need to answer this question. So we performed the numerical simulation. So three cases. One is the normal case. So without burning room temperature droplet. And so this is the first case. And another case is we model a hot droplet. However, the droplet has a uniform surface temperature, means that we do not have thermal capillary flows. So this is the second. And the third case is that the surface tension is a function of the temperature. So the droplet is in a high temperature, impact onto a cold solid wall. In these three cases, we only observe bouncing of the droplet for the last case, means that we have a high temperature droplet, and also the surface tension depends on the temperature. So from the numerical simulation, we found that when a hot droplet is approaching to a cold surface, it cools unevenly, means that the bottom cools faster than the other regions of the droplet. So there will have a temperature gradient along the surface of the droplet. And then this will create a surface tension gradient and to induce a so-called Marangoni flow. So here we call them as a thermal capillary flows. So here, given that in the middle droplet, the middle bottom droplet, the temperature is lower. In the outside, the perimeter of the droplet, the temperature is higher, so that the direction of the thermal capillary flow is from the outer to the inner of the within the droplet. So we have this circulation from the outer to the inner. So with this kind of thermal capillary flows, it will induce additional attraction of air along this salvaged gas layer. So this means that additional air is supplied into this gas film. So this additional airflow will be responsible for stabilizing the gas. So this is the reason. And also we investigated the evolution of the gas film. We found that in our hot droplet case with the thermal capillary flow, the gas film is always getting thicker when in both the spreading and the receding stages. However, droplet, and also for the hot droplet with constant surface tension, the gas film is getting thinner and thinner. Means that the gas film is squeezed by the impacting droplet. And then at the same time instant, the gas film collapses. So we also observe this thermocapillary flow, this vortex within the burning the hot droplet. So so for example, in the particle imaging system, this is a normal droplet. We observe no vortex. However, for a burning droplet, so here we see that after the bouncing of the droplet, we see a vortex, a pair of the vortex inside the droplet, and also it occurs for hot droplet shown up here. After the bouncing, we see a pair of vortex here. So this indicates the presence of the thermocapillary flows. Okay, so this is our explanation and understanding on the mechanisms for the enhanced gas film. And finally, we propose that how can we make use of this phenomena? We designed two experiments. One is that we have a superhydrophobic surface, and we release a burning droplet onto this superhydrophobic surface. We found that compared with the superhydrophobic surface, the so here is a control group, hydrophilic surface, copper surface. So we found that compared with the pristine copper surface, the super amphiphobic copper surface can sustain the burning state of the droplet for an extended time. So the combustion duration will be enhanced by at least 200 times, and sometimes can so it is enhanced by 2 to 3 orders of magnitude. So this means that probably we can use the superhydrophobic coatings to enhance the combustion efficiency of the fuel droplets in some scenarios, an engine or some other applications. And also in another application, we coat our super amphiphobic coating to a plastic. So this plastic, for the pristine plastic, the burning droplet will stay on the plastic, and it will burn on the plastic, so that the high temperature will destroy the plastic. However, on our super amphiphobic surface, the burning droplet will be easily shaded away, so that it can protect the plastic, the substrate, the bottom substrate, from the burning of the droplet. So we propose that probably we can develop some novel fire retardant coatings by using super amphiphobic coatings. So these are some perspectives that can be inspired from these works. So in summary, for this combustion, burning and hot droplet case, the anisotropic capillary effect roots in the thermocapillary flows because of the localized cooling of the droplet, so that the thermocapillary flows, they are localized. And then it will induce the different flow behaviors within the gas film, so that the bouncing behavior of the droplet is totally changed from the sticking state to the bouncing state. Okay, so yeah, so here I would like to thank my group members and also my collaborators, and also some financial supports from different agencies. And so this is my total presentation today. Thank you for your attendance. I'm happy to receive any questions.
Yeah, thanks a lot for Professor Zhu's excellent presentation. Yeah, I'm thinking, yes, it's very interesting. And also here are some questions. And Professor G, just now, yes, I show Professor G's question first. Why is the liquid repellent copper plate, the combustion duration is much longer?
Yeah, so here, okay. So here on this video, we can, so probably I will need to, okay. So on this video, yeah, so on this video, we see that on this superhydrophobic coated copper plate, the droplet is always burning because the contact between the droplet and our coating is very minimized. So it means that the droplet cannot be cooled down very fast. So because there is a gas layer between our droplet and the solid surface so that the droplet can maintain a high temperature for the combustion. However, for the pristine copper, the droplet will very fast spread along the solid surface so that they are spreading. So here we can see that. So its spreading film is from here to here. So a very large film is formed on the copper surface. So the liquid can be cooled down very fast in this process. And then with a very fast drop in the temperature within the droplet, and then the burning state cannot be maintained because the temperature is too low.
Professor G, yes, yeah, you did all right.
Yes, it's good. I understand that.
Okay, very good. And Professor G's second, another question is that I know you use surfactant to generate hollow droplet. In this case, how does surfactant affect the droplet dynamics? Does this Macaulay effect matter? Or is very fundamental, professional, I'm thinking here. Very good question.
Yeah, very good question. Because Professor G is an expert in the bubble dynamics. So here I would like to say that yes, we use surfactant to stabilize the bubbles. So for our bubbles here, the lifetime can be as long as tens of seconds, and in some cases can be several minutes. And so we didn't consider the Marconi effect in this experiment because for one reason the temperature is constant, so there is no thermal capillary flows. But on the other hand, the concentration distribution of the surfactant can also induce the Marconi effect. But here we didn't consider that. We didn't. So the surfactant we use is SDS. Is ionic surfactant. They are small molecules. Uneven distribution of the surfactant. Yeah. So this is from our experiment, and also in our numerical simulations, we didn't consider the Marconi flows, but still we observe the same bouncing situations. Yeah.
And he also asked, will the position of the particle affect the impact behavior of droplet? How to control it?
Okay, so yeah, also a very good question. So actually, in this case, in this experiment, the position of the we didn't intended to have a very so we do not need to carefully control the position of the particles, because here the particles we use is a spherical particle. So we use microfluidics to produce these spheres. So they are very uniform. And because the density difference between our particles and the liquid layer, so naturally the particle will be slightly at the bottom of the droplet. So they will always be there, okay? We would also to have, for example, to consider to reduce the density of the particles so that the particle can stay on top of the solid, on top of the liquid droplet. However, in practice, in our lab, we found it to be challenging to achieve this. But from my perspective, if there is a density difference, for example, the particle is lighter than the liquid shell, the position of the particle will finally change the three regimes of the droplet. Because in the first regime, it requires the solid-solid contact. So when the droplet stays on top of the, when the particle stays on top of the droplet, so it will be very challenging to achieve the solid-solid contact first. However, in the later two regimes, means the partial retraction regime and the complete retraction regime, possible when we change the particle position within the droplet. Yeah.
So I also have a question, Professor Yang.
Yeah, please continue. Okay. Yeah.
So also for this example for the particle laden droplet, I'm wondering. So you use a superhydrophobic surface here, right?
In most cases, yes. But we also use the other surfaces. Yeah.
if it's hydrophilic, so will it change the impact behavior of the droplet? Usually, droplet cannot bounce at a hydrophilic surface. So if you insert a particle in the droplet where the droplet bounce.
Yes, a very good question. So my answer is yes. Indeed, we have performed this experiment. But it will depend. So again, it will depend the position of the solid particles. So in some case, if the solid particles do not touch the solid substrate first, means that the liquid solid contact occurs first, and then the droplet will be sticking on the solid surface, right? However, if again in a superhydrophilic case, a solid firstly touch the bottom substrate, and then there is still a chance this particle-laden droplet will bounce away. Yeah.
Okay. Very nice. Thank you.
Yeah. Thank you for the very good question.
Yes, I also have some questions. Although compared to Professor G, my question is not very professional, but I'm very interested in your topic actually. And first, you at the beginning of your presentation, you mentioned the spring. The two springs actually, you just consider spring as this effect of the droplet with this wall rebumblings. Do you how to describe the spring? Maybe you can using some modeling, use a model to describe the effect of the spring, the force, to based on the spring, yes, there's some effect on the droplet. You can describe it in the model.
Thank you. Yeah, thank you, Professor. So this is a very deep and very good and very hard, difficult to solve the question. Indeed, in our paper, we developed a very simple model to account for the effect for these two springs. But here, I didn't put the equations here. So our consideration is also very simple. Given that these two, so we have these two springs has the length and the spring constant. L indicated the length, K indicated the constant. So here the K is modeled by the surface tension gamma, and L is modeled by the surface area, S, or the radius of the droplets and bubbles. So with this method, we can model this two double spring system into our hollow droplet system. And our consideration is very simple. So given that these two springs, their effect is opposing with each other, so we directly find an effective stiffness of the spring by reducing the effect from the two. Okay, so yeah. So with this case, we can define. Let me check whether on the second page we have the equation. Okay, I don't think so. Initially I have the page, but for today's presentation, it does not here. But in our paper, we did this. We define an effective surface tension. So this effective surface tension is reduced. So, and this explains why we observe and inhibit bouncing for the droplet, because we can still use this inertia capillary time scale to explain the problem. For example, in our hollow droplet case, the effective surface tension here, gamma, is reduced. So this value is reduced, and then the total tau is increased. And given that the TC equals a constant ratio of the tau, so the tau increased, and then the contact time is greatly increased. And now we can consider an extreme case when this gamma is diminishing, means gamma is approaching to 0. This tau is approaching to infinity. So the contact time is approaching to infinity. Contact time approaching to infinity means that the droplet will not bounce. It will always stay on the surface. So this is consistent with our observation. Yeah.
Okay. Yes, I will study your paper to get the questions. Why I ask you the questions? Because in the particle areas, we using the DEM. The DEM, yeah, discrete element method to consider the particles impact. Also, that spring there, using the just using spring to describe the interaction of the particles. So I'm just now I'm wondering maybe you can use in similar methods to consider the problems of the droplet and the war and yeah, this is very good. Yes, the modeling their methods maybe can help you to give more in-depth mechanisms of it. Yeah.
Yeah, and, thank you for the suggestion. Yeah.
Yeah, and I'm very interested in your presentation later. You have many different droplet. For example, you have icing droplet and a boiling droplet and a hot droplet. Yes, I feel some confusing actually. You mentioned one by one. Yes, very complex and very interesting. Can you here give us some very brief introductions? What's the difference of them, and particularly boiling droplet and hot droplet? What's the difference? Because they're also boiling. I'm thinking is also hot, but based on the different temperature actually. Yes. Can you please give us some a brief introduction again? Yes, of these three droplets. Yeah.
Okay, sure. Thank you for the question. So here I will start from the burning and hot droplet. So the burning droplet means that the droplet is a fuel droplet and the liquid is burning. So there is a combustion. So there is a flame. The hot droplet means that the liquid is not ignited. Means that only the temperature is increased. Yeah. For example, here we control the hot droplet in most of our experiment to be 120 degree. However, this droplet, for example, using hexane decay, we only heat the hexane decay to this temperature, but without igniting the droplet. So this is the major difference between the burning droplet and the hot droplet. Yeah. So as for So as for the other case, they have different different structures, right? We have core shell structures, so they are different from this very this uniform single phase droplet. Yeah.
So here I'm thinking that your question actually considers very complex. You consider the solid and also some temperatures here. So you need to consider the fluid, need to consider the heat transfer, and yes, you are right. You also need to consider the phase changing actually. Yeah. There are many problems you should be considering in the future actually. Yeah.
Yes, you are very right. So initially, I was very frustrated. I thought we cannot solve this problem. Means that we don't know the exact reason why the enhancing occurs. So because as you mentioned, a lot of physical chemical processes occur. But later, very luckily, we found the very key influencing parameter, means that the temperature only. So here we can exclude a lot of parameters, at least for this study. So here I need to say that this is a very preliminary study. So as Professor Yao mentioned, a lot of future works need to be done to give a very full picture regarding what happens for this Berlin droplet dynamics, especially considering about the combustion process and also a lot of phase change process, the vaporization, the condensation. Yeah, we do observe condensation within our system, and also the chemical reaction process, the heat transfer process. But I think it's very challenging. At least for me. So I hope that I can initiate some collaborations with well-established scholars here to help me to solve this problem. Yeah.
Yes, near the end of this today's keynote meeting, and I, on behalf of IMFTF and other people and all of this attendance of this meetings, thanks the Professor Ji and Professor Zhu give us excellent presentation today. And I'm thinking some of the people will have some questions. You can direct contact Professor Ji and Zhu by email or by their WeChat. And by now, I just noticed that today's presentation already have more than 232 persons here and attend your presentations. And I will also transfer your presentation to all of these IMF academic members and previous speakers, around more than 60 people there around of the world. I'm thinking through this presentation, hopefully your work will get more noticed and more impact in these areas. And again, thanks to Professor G and Professor Zhu very much. And today, our meeting is finished, and the Zoom will be closed quickly. So see you later. See you later in next IMFTF the presentations in next month. And welcome everyone come back to attend our activities. Thank you very much, and goodbye.
Okay, thank you, Professor Yao. Yeah. Bye.
Bye.
Yeah.
Thank you.
Yeah.
Thank you very much.
Yeah. Okay, thank you. Bye. Yeah.